Welcome to this coding walkthrough. Today, we will tackle an exciting problem: remove all adjacent duplicates in string 2. This problem challenges us to manipulate strings efficiently while adhering to specific rules. Get ready to dive into the details and learn some clever approaches to solve it. In this problem, you're given a string S composed of lowercase English letters and an integer k. The goal is to repeatedly remove groups of k-adjacent, identical characters from the string. This process continues until there are no more such groups left in the string. Once all the removals are done, you return the final string as the output. The problem guarantees that the resulting string will be unique, meaning that no matter how you perform the removals, the final result will always be the same. The input size can be large, with S having up to 100,000 characters and k going up to 10,000. So an efficient solution is important here. To understand this better, let's look at some examples. In the first example, the input string is S equals ABCD and K equals 2. Since there are no adjacent duplicates in this string, there are no groups of size K to remove. As a result, the output remains the same as the input, which is ABCD. This demonstrates a case where no removals are necessary, and the string remains unchanged. Now, consider the second example, where the input string is S equals D and K equals 3. Here, we can remove groups of 3 identical characters in a step-by-step process. First, the 3 consecutive ES are removed, leaving us with DBKBDA. Then, the 3 CS are removed, resulting in BIBDA. Next, the 3 BS are removed, giving us DA. Finally, the 3 DS are removed, leaving only AA as the final output. This example shows how the process can involve multiple rounds of removal until no more groups of size k remain. In the third example, the input string is S equals sites with k equals 2. Here, we start by removing all pairs of adjacent characters. First, the pair of BS is removed, leaving sites. Then, the pair of GS is removed, resulting in siapoepoes. Next, the pair of TS is removed, giving siapoepos. Following that, the pair of IS is removed, leaving xapuus. This process continues step by step until we eventually reach the final output string of PS. This example demonstrates how repeating the removal process iteratively can simplify the string down to its final form. Finally, it's important to consider some constraints and edge cases. The length of the string can go up to 100,000, and k can be as large as 10,000. So handling large inputs efficiently is crucial. An edge case occurs when k is larger than the length of the string, as no groups of size k can exist, meaning the output will always be the same as the input. Similarly, if the string has no groups of adjacent duplicates, no removals are made, and the output remains unchanged. In cases where groups overlap or need to be removed multiple times, the process must continue iteratively until no more valid groups remain. Additionally, smaller values of k lead to more frequent removals, as smaller groups of adjacent duplicates are easier to find and eliminate. To solve this problem, we first considered a brute force approach. The intuition behind this method is straightforward: repeatedly scan the string for any groups of k consecutive identical characters and remove them. This process is repeated until no such groups remain. While this method is simple to implement, it has a major drawback. Each scan of the string takes n time, and since the string is modified repeatedly, the overall time complexity can escalate to n squared, or even worse for larger inputs. This makes the brute force approach highly inefficient and impractical for large strings. Instead, we can adopt an optimized solution using a stack. The intuition here is to process the string character by character, leveraging the stack to efficiently track characters and their frequencies. For each character, we first check the top of the stack. If the stack is empty or the character at the top is different, we push the current character along with its frequency, which starts at 1. However, if the top character matches the current one, we simply increment its frequency. If the frequency reaches k, we pop the character from the stack, effectively removing the group of k identical characters. Finally, once all characters are processed, we can reconstruct the resulting string from the stack. This approach is much more efficient, with each character being pushed and popped from the stack at most once, resulting in an overall time complexity of n. The space complexity is also n due to the stack. The key observation that makes the stack-based approach efficient is realizing that instead of repeatedly scanning and modifying the string, we can use the stack to directly manage the removal of groups of k identical characters. By storing both the character and its count in the stack, we eliminate redundant scans and modifications, significantly improving performance. This insight was the aha moment for this problem. Now, comparing this approach to the alternatives, the brute force method, though simple to implement, becomes computationally expensive as input size grows, due to its repeated scans and modifications, which can lead to a time complexity of n squared, or worse. On the other hand, the stack-based approach processes the string in a single pass and uses auxiliary space to efficiently track character groups, achieving a time complexity of n, and a space complexity of n. While the stack-based solution may be slightly more complex to implement, its efficiency and scalability make it the clear choice for handling larger inputs. This trade-off highlights why the stack-based approach was chosen over the brute force alternative. The problem here is to repeatedly remove groups of k consecutive identical characters from a string until no such groups remain. The goal is to return the resulting string after all these removals. To solve this efficiently, we use a stack-based data structure. The stack helps us keep track of characters and their consecutive counts as we process the string. Each entry in the stack is a pair containing the character and the count of its consecutive occurrences. By using this approach, we can avoid repeatedly scanning the string, which makes our solution more efficient. Now, let's talk about how we process the string using the stack. As we traverse the string character by character, we handle three main cases. First, if the stack is empty, we simply push the current character along with a count of 1 onto the stack. Second, if the character at the top of the stack matches the current character, we increment its count. If this count reaches k, it means we have k consecutive identical characters, so we pop that entry from the stack, effectively removing the group. Third, if the top of the stack contains a different character, we push the current character with a count of 1 onto the stack. Once all characters are processed, the remaining entries in the stack represent the unremoved characters and their counts. At this point, we use the stack to reconstruct the final string by repeating each character based on its count. The stack is a crucial part of this algorithm because it allows us to efficiently manage groups of consecutive characters. With each push and pop operation taking constant time, the stack ensures that we don't need to repeatedly scan the string, which significantly improves efficiency. Compared to a brute force approach that would scan and remove groups multiple times, resulting in n squared complexity, the stack-based method reduces the complexity to n, since each character is processed only once. Additionally, the algorithm handles edge cases such as an empty input string, strings with no groups of size k, or strings that completely collapse into an empty result. The stack also ensures that overlapping groups are handled sequentially, preserving correctness. To implement this algorithm, the stack is the central data structure. It stores pairs of characters and their counts, allowing us to efficiently track consecutive occurrences. Let's walk through an example with the input string s equals d and k equals 3. We start with an empty stack and process each character in the string. First, we push d1. Then, for the next 3 es, we increment the count to e3 and remove the group since the count equals k. We continue processing, pushing new characters or incrementing counts as needed. After processing all characters, the stack contains d1, 2. From this, we construct the resulting string by repeating each character based on its count, giving us AA as the final result. In terms of time complexity, the processing step takes n, because each character is pushed and popped from the stack at most once. Constructing the result string also takes n, as it depends on the number of characters left in the stack. Therefore, the overall time complexity is n. For space complexity, the stack requires n in the worst case, such as when no groups are removed and all characters remain in the stack. Thus, the overall space complexity is also n. This balance of time and space complexity makes the algorithm both efficient and practical for large inputs. This Python implementation solves the LeetCode problem: remove all adjacent duplicates in string 2 using a stack-based approach. Here's a detailed step-by-step explanation. 1. Initialization. The function remove duplicates takes two inputs, the string s and an integer k. A stack is initialized as an empty list to help track characters and their consecutive frequencies. 2. Iterating through the string. The loop iterates over each character in the string S. If the stack is not empty and the top of the stack contains the same character, the frequency count is increment. When the frequency count for a character reaches k, the character is removed, popped, from the stack. 3. Pushing new characters. If the current character does not match the top of the stack, it is added to the stack with an initial frequency of 1. 4. Reconstructing the result. After processing the entire string, the stack contains characters and their remaining frequencies. The final string is reconstructed by multiplying each character by its frequency and joining them together. 5. Edge cases. The function handles cases where no duplicates exist or when the string is empty. It also accounts for strings that repeatedly require removal of adjacent duplicates. This approach is efficient with a time complexity of O(n), where n is the length of the string, as each character is processed once. The space complexity is O(n) in the worst case for the stack storage. Here, we start by importing the necessary libraries and defining our solution class. The main method, removeDuplicates, takes in the input string s and an integer k, which represents the threshold for removing adjacent duplicates. To solve this problem, we use a stack that stores pairs of characters and their frequencies. The stack is implemented using a deque, specifically an array deque, for efficient operations. The logic begins by iterating through each character in the string. If the stack is not empty and the top character on the stack matches the current character, we increment the frequency of the character on top of the stack. If the frequency reaches k, it means we have k adjacent duplicates, so we remove this character from the stack using the pop operation. On the other hand, if the stack is empty or the top of the stack does not match the current character, we simply push a new pair onto the stack, consisting of the current character and an initial frequency of 1. This ensures that we are tracking contiguous groups of characters and their counts. After processing all the characters, we reconstruct the final string from the stack. To do this, we use a string builder to accumulate the result. We iterate through the stack in reverse order, appending each character multiplied by its frequency to the result. This step ensures that the characters appear in the correct order and with the right counts. Once all pairs from the stack have been processed, we convert the string builder to a string and return it as the result. Finally, the pair class is defined as a helper class to store each character along with its frequency. It has two fields, character and count, and a constructor to initialize these fields. This class helps us encapsulate the character and its frequency together, making the stack operations more intuitive and maintainable. With this implementation, we efficiently remove adjacent duplicates in the string while adhering to the given constraints. To begin solving this problem, let's look at example 1 where the string is ABCD and k is 2. First, we initialize an empty stack to help us track characters and their consecutive frequencies. As we process the first character A, the stack is empty, so we append A1, indicating that it appears once. Moving to B, the top of the stack contains A1, which does not match B, so we append B1. Next, we encounter C. Again, the top of the stack does not match C, so C1 is appended. Finally, we process D. Since D doesn't match the top of the stack, we append D1. At this point, the stack contains A1, B1, C1, D1, which means no adjacent duplicates were found that need removal. Now that we have processed all characters in the string, we reconstruct the result by combining each character with its respective frequency from the stack. In this case, we have A*1, B*1, C*1, and D*1. When joined together, the final result is the string ABCD. Let's move to example 2, where the string is D and k is 3. Here, we start with an empty stack. The first character D is appended as D1. Next, we process E, appending it as E1. When the second E is encountered, we increment its frequency to E2. On the third E, the frequency reaches k, so we remove it from the stack, leaving D1. This demonstrates how the stack helps us remove adjacent duplicates efficiently. After removing E, we resume processing characters. The next D matches the top of the stack, so its frequency is increment to d2. Then, we encounter b, which does not match the top, so we append b1. The next b increments its frequency to b2. Moving to c, we append c1, and subsequent c characters increment the top frequency to c2, and then c3. Since the frequency reaches k, we remove c from the stack, leaving d2 b2. Afterward, another b increments its frequency to b3, causing it to be popped from the stack as well. This iterative process ensures that groups of k duplicates are removed as soon as they are detected. With the stack now at d2, we process the next d, incrementing its frequency to d3. Since this reaches k, we pop d from the stack, leaving it empty. Next, we encounter a, appending it as a1, and then another a, incrementing its frequency to a2. Finally, we reconstruct the result from the stack, which contains only a *2, resulting in the string AA. This example showcases how the algorithm dynamically adjusts the stack to remove duplicates while preserving the order of characters that don't meet the criteria for removal. For the final example, we analyze the string *sites with k set to 2. Starting with an empty stack, we append p as p1. Next, b is appended as b1, and the following b increments its frequency to b2, causing it to be removed. This pattern continues for each character. Groups such as GG, TT, and 2 are removed as their frequencies reach k. After processing all characters, the stack contains S1. Reconstructing the result gives S, as all other adjacent duplicates have been eliminated. This concludes the walkthrough, illustrating how the stack efficiently handles removal of adjacent duplicates in a scalable manner. To analyze the time complexity of this algorithm, let's break it down into its individual components. First, the algorithm traverses the input string s using a single for loop, which means each character is visited exactly once. Given a string of length n, this traversal contributes O(n) to the overall time complexity. Next, we consider the operations performed on the stack. When a character is added to the stack, it takes constant time, or O(1). Similarly, updating the frequency of a character or removing it from the stack when its frequency reaches k also takes O(1). Since each character is pushed to and popped from the stack at most once during the loop, the total contribution of stack operations remains O(n). Finally, after processing the string, we reconstruct the result by iterating through the stack to concatenate characters. Since the stack size is proportional to n, this step also takes O(n). Therefore, when we combine all these parts, the time complexity of the algorithm is dominated by O(n) at each step. Now, let's summarize the overall time complexity. Adding up the traversal, stack operations, and result reconstruction, we get O(n) plus O(n) plus O(n), which simplifies to just O(n). Next, we analyze the space complexity. The primary space usage comes from the stack, where we store pairs of characters and their frequencies. In the worst case, if no duplicates are removed, the stack could grow to hold all n characters, contributing O(n) to the space complexity. Additionally, the result string we construct from the stack will also have a size proportional to the length of the input string, contributing another O(n). Finally, apart from the stack and the result string, the algorithm does not use any significant auxiliary space. Combining these contributions, the total space complexity is O(n) for the stack, plus O(n) for the result string, which gives us a final space complexity of O(n). Let's take a closer look at the best, average, and worst-case scenarios for this algorithm. In the best case, if the value of k is greater than the length of the string n, no duplicates are removed because the frequency condition cannot be met. In this scenario, the algorithm simply traverses the string, resulting in O(n) time complexity and O(n) space complexity. In the average case, some duplicates are removed during processing, reducing the effective size of the stack. However, the overall behavior of the algorithm remains the same asymptotically, with both time and space complexities staying at O(n). In the worst case, no adjacent duplicates are removed, meaning the stack grows to its maximum size and holds all n characters. Even in this scenario, the algorithm still operates with O(n) time and space complexity. By comparison, a naive approach that repeatedly scans the string to remove duplicates would involve multiple passes over the input. This could result in a time complexity of O(n) squared in the worst case, though it would use only O(1) space beyond the input string. This stack-based solution is optimal because it processes each character in the input string at most once, achieving a linear time complexity of O(n). The space complexity of O(n) is also efficient, as it only depends on the size of the input string and the result. When compared to the naive approach, which can require multiple passes through the string and thus result in quadratic time complexity, the stack-based method is a significant improvement. By efficiently managing characters and their frequencies with a single traversal and minimal space usage, this solution strikes an excellent balance between time and space, making it well-suited for handling strings of any reasonable size. When solving this problem, there are several common mistakes to be aware of. First, you need to handle edge cases properly, such as when the input string is empty or shorter than the required group size k. Neglecting these cases can easily lead to runtime errors. Next, avoid inefficient repeated traversal of the string. Solutions that scan the entire string multiple times looking for groups of k identical characters can result in poor performance, with time complexity ballooning to O(n) squared or worse. Instead, a stack-based approach can significantly optimize this process. Another frequent pitfall is not updating the stack correctly. For example, if you remove a group of k characters, forgetting to adjust the stack or the frequency of remaining elements can lead to incorrect results. Lastly, it's important to fully understand the removal process. Some implementations mistakenly remove only one instance of the group instead of deleting all k characters in a single operation. Always ensure that the entire group is handled in one step. Now, let's consider other potential issues and insights. One mistake is assuming the input is always valid. While this problem typically deals with alphabetic characters, you may encounter unexpected inputs or non-alphabetic characters, especially if constraints aren't clear. Validating inputs can help prevent failures in such cases. From an interview perspective, this problem is often used to test your ability to recognize patterns in the input and apply efficient data structures like stacks. Interviewers might challenge you with variations, such as dynamically changing the value of k or handling nested groups. They also value candidates who can optimize solutions. You might start with a brute force approach to demonstrate your thought process, but it's crucial to quickly pivot to an optimized method, like a stack-based solution, to highlight your understanding of efficiency. Additionally, be prepared to discuss edge cases, such as when the input string is empty, k is very large, or no removable groups exist. These discussions show your attention to detail and robustness in problem solving. This problem is also connected to several related challenges. For instance, LeetCode 1209 focuses on removing adjacent duplicates in a string, but you might also explore LeetCode 1047, which deals with removing all adjacent duplicates, or LeetCode 316, which involves removing duplicate letters while maintaining lexicographical order. Another interesting connection is LeetCode 735, the asteroid collision problem, which also leverages a stack-based approach for handling sequences. As for alternative approaches to solving this problem, the stack-based method is the most common and efficient, with a time complexity of O(n). However, it does require extra space for the stack. A two-pointer approach can also achieve O(n) time complexity while using less space, but it can be more challenging to implement correctly and debug. Lastly, there's the in-place modification technique, which reduces space usage but is significantly less efficient, with a worst-case time complexity of O(n) squared. While not ideal for large inputs, understanding these trade-offs can help you choose the best strategy in different scenarios. Great job following along. Today, we learned how to solve the remove all adjacent duplicates in string 2 problem using a brute force approach. Remember, efficient string manipulation is a key skill for many coding challenges. Keep practicing, and don't forget to subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!